Today we will move on to lesson 3, light matter interaction. Okay, this is a lesson before we can focus on the second type of post-generation technique, the passive locking. Okay, this lesson is divided into 4 sections. The first 2, including saturable absorber and the dynamic gain, you can see the terms absorption and the gain. So they are about amplitude modulation. And the third and the last sections are about such as cell phase modulation and the group velocity dispersion. You can know by these terms that the last 2 sections are about phase modulation. Okay, so they can be categorized into amplitude and the phase modulations respectively. Okay. And the motivation of this lesson is we will first focus on how to model different light matter interaction mechanisms, including the 4 types of mechanisms. But they are just tools. The interplay among these mechanisms and how to use them to generate pulses shorter than those of active locking will be discussed in lesson 4. Okay? So after we know all the mechanisms, we will be able to discuss how to generate even shorter pulses from picosecond regime to femtosecond regime. Okay. But that will be the topic of next lesson. So let's start with saturable absorber. Okay. We will deal with saturation model and then try to solve analytic solutions for 2 extreme cases, including the phased saturable absorber and the slow saturable absorber. Okay. Physically, we will encounter the absorbers we will encounter belong to either fast or slow saturable absorbers. But in theory, they can be something in between. But in that case, there is no analytic solution, which is more complicated. So we will only focus on the 2 extreme cases. Okay. So from this slide, you can easily identify this is the well-known 4-level system, 4-level model we have used in lesson 1. Level 1 is the ground state. Level 2 is here. Level 3, level 4. This is the well-known 4-level systems. So there are, we have seen this formula before. In lesson 1, we define the stimulated emission rate of the gain medium in this way. Okay? S, stimulated emission rate, equals sigma g, the effective cross-sectional area, depending on the material, times I is the light intensity, over U0. U0 is defined here, single photon energy. And this is so-called stimulated emission rate. Do you still remember the meaning of stimulated emission rate? Okay. Based on the physical units, 1/second. So this parameter specifies the percentage of electrons on level 3 stimulated to level 4 in 1 second. Okay? So the larger this number, the stronger stimulated emission occurs. Okay? But this is what we used for gain medium, right? Which we used in lesson 1. But here, we are interested in absorption instead of gain amplification, right? So we can borrow the stimulated emission rate formula, which we used before in this way. So we define stimulated absorption rate the absorber with a symbol of A. A means absorption, absorber, equals sigma A, okay? So very like sigma G. So it represents the effective cross-sectional area of the absorber, okay? Times I, but I is replaced by P over A, right? I is the intensity or power density, the power per unit area. So it's equal to the instantaneous power, P of T, divided by beam cross-sectional area, A sub A, okay? And the U0 is preserved, okay? Then we can define the stimulated absorption rate, just like stimulated emission rate as before. The only difference is now SA relates levels 1 and 2 about the absorption. And the S relates level 3 and the level 4. It's about amplification. That's the only difference. And in lesson 1, we have known the concept of gain saturation, right? What is gain saturation? Every time you got a new photon by stimulated emission, you pay the price. One upper state electron translates to a lower level, so you lose some amplification capacity. Here is the things are the same, okay? Whenever you got absorption, you pay the price, because now the number density of ground state, which is level 1 here, will be smaller, okay? So you will lose some absorption capacity as well. So this is the something we have known before. Okay, any question? And very like the assumptions we made in lesson 1. Now we assume relaxations from level 2 to level 3, which is here, and the relaxation from level 4 to level 1, which is here, are both very fast. So they have very short lifetime constants, okay? And we also designate the transition between levels 3 and 4 here. But this time, the material is absorber. It's not a gain medium. So the relaxation here is not about stimulated emission. It could be about spontaneous emission or some heat process, okay? And it's described by a lifetime constant tau sub A. And again, here, tau sub A is much longer than tau 23 and tau 41, because we have assumed the two relaxation processes are very fast compared with the natural relaxation between levels 3 and 4. Okay. We made the same assumption before when we talk about gain medium. Now, we can borrow what we have obtained before. You can use the same technique to write down 5 rate equations. The 5 rate equations can be used to solve 5 unknown functions, including the number densities of all the levels, n sub 1 all the way to n sub 4, as well as the stimulated absorption rate S sub A. You have 5 unknown functions. And I skip the process to write down the 4 rate equations because you have seen before in lesson 1. So these are the 5 rate equations. For example, let's check equation 1. Why is equation 1 valid? N1 dot means time derivative of number density of level 1. Okay? And it depends on 2 mechanisms. One is stimulated absorption from level 1 to level 2, right? So you will lose number density. That's why you have a minus sign here, okay? And the second process is about relaxation from level 4 to level 1, so you will gain some number density. That's why you have a positive sign here. Okay? And the combination determines the rate change of number density on level 1. So you can apply the same strategy to all the 5 rate equations. Okay. And again, equation 5 simply specifies that total number density is a constant. The electrons can only be redistributed among these 4 levels. No electrons can be created from nothing, and no electron can be lost. Okay? So the total density is a constant n sub a, determined by your material. Okay. But there is one thing different compared with what we did in lesson 1. Remember, in lesson 1, we are only interested in steady-state solution, right? We don't care about the dynamics. But here, we care about dynamics. So we cannot just try to solve the steady-state solution. Okay? We need to take care of the time evolution. Okay? A function of time. This property has to be preserved. But the central issue of this part is the dynamic field loss coefficient. Okay? Very like what we have seen in section 1-3. At that time, we define the field gain coefficient instead of loss coefficient. Right? Gain coefficient is defined here. Okay? I believe you can identify why is that. It roughly means the output electric field, okay, is equal to the input electric field times e to the g. Okay, g is in the exponent. That's why it's defined as gain coefficient. At that time, gain coefficient is roughly equal to n3, which is number density of level 3, times equivalent volume, Vg, okay, constant 2, okay, and the Vg is the effective gain cross-sectional area times the interaction length, Lg. Okay. Here, it's very similar. The field loss coefficient, L, is defined in this way. There is a minus sign because now the output is smaller than the input due to the loss. So you need a minus sign. The only difference is N3 is replaced by N1 because now it's the transition from level 1 to level 2 matters. Okay? So how strong you can absorb depends on number density N1 instead of number density N3. This is about gain, amplification. Here, we are interested in absorption. So N1 matters. The larger the N1 you have, the stronger the absorption you can have. Okay? Everything else is very similar. Replace Vg by Va. Va is an equivalent volume, which is equivalent cross-sectional area, sigma A times absorption length, L sub A. Okay, so it's very clear. If you want to know the loss dynamics, say you want to know L of t, what is the loss coefficient, L, as a function of time? What do you need to do? Trying to solve N1 as a function of time. Okay. Okay. Just like previously, when we try to solve the gain coefficient G, all you need to do is try to solve N3, right? But now we need to solve N1 instead of N3. Okay, so it's a repeat of the 5 rate equations. Starting with equation 5, we know the number densities N2 and N4 are relatively small compared with N1 and N3. Okay, do you still remember the reason? because the fast relaxations. Okay, good. So for that reason, you can simplify equation 2 in this way. N1 plus N3 is close to NA, a constant NA. Besides, you can eliminate N4 dot. Okay? If that is true, you can relate N3 and N4 in a simple relation. But why can we eliminate N4 dot? It's different from the reason we encountered in lesson 1. In lesson 1, we were interested in steady state only. If you are interested in steady state only, all the time derivatives, not just N4 dot, okay, N1 dot, N2 dot, N3 dot, N4 dot, can all be eliminated, right? But here, we need to take care of dynamics. So in principle, we cannot just eliminate Ni dot, okay? But why? Here, we can eliminate N4 dot. Why this term can be approximated by 0? Yes, please?
Because all the electrons dropping from level 3 to level 4 is quickly drop back to ground state.
Good, okay. Still, the fast relaxation, okay? So let's go back to the figure here. Because of the fast relaxation, okay, any electron dumped to level 4 from level 3 will be quickly dumped to level 1. So 1 in, 1 out immediately, okay? So there is no rate of change on the population of N4. So you can eliminate N4 dot. Not eliminate N4 itself, but its time derivative. Okay. Okay. Then we can use the simplified equation 4, apply it into equation 1, because in equation 1 we have a ratio N4 over tau 4y, which is here. Now you can replace it by N3 over tau A. Okay? So you will not see N4 anymore. Okay? After that, you got this equation. N1 dot is close to minus SA times N1 plus N3 over tau A. But this is not good enough because you still have two unknown functions, N1 and N3. Okay? Hopefully, we can simplify the equation to a single unknown function. Okay? So N3 is not what we desire. Okay? Now, we can further simplify this equation by replacing SA and N3 by something else. This is quite easy, right? You just borrow the definition of SA. How about N3? Is there any relation between N3 and N1, right? Because in the end, we hope an equation with single unknown function, N1 only, right? So what can you do? You can borrow this relation. So if you do that, you can have SA replaced by definition. N3 is replaced by NA minus N1. Okay? Now, you have only one unknown function, N1, right? And the N1 is the only unknown function we intend to solve. Because once you have N1, you can know the loss coefficient, right? So this is the final equation we obtained. The only new definition we introduced is replacing sigma A U0 AA by this way, PA tau A in the denominator, where the PA is a new parameter, absorption saturation power, defined in this way. Okay? Clearly, this is a parameter about power because U0 is the single photon energy. Tau A is the lifetime. So energy divided by time, this is power, right? And how about this one? This is beam cross-sectional area. This is equivalent cross-sectional area of your material absorber. So both are about areas. So the ratio is constant without physical unit. So this is something about power. We define it as absorption saturation power. Okay. By using this definition, you got the rate equation, a differential equation with single unknown function n1. n1 is here, here, and here. Nothing else, right? Question?
就是 n 次 dot 它等于零的原因，觉得怪怪的，因为它的那个 n 次的 changing rate， 那可是你说因为 n3 掉到 n4的那个它的那个 i 很快就掉到 ground state， 然后所以这样它的 changing rate 是零，可是感觉应该。 如果它的就是它感觉是它一瞬间有，然后马上没有，但是这不是表示确率是很大的意思。
Yeah, good point. You can think about it.
你就是因为你进去的进去的角度出来多少，因为就是正和负3的时候，就是这样的。
It's something about dynamic balance 啊，动态平衡的概念。 就是你微观上看可能是有进有出的，但你巨观上看它好像是没在动。我们动态平衡的概念是如此。这边借用的是这个概念。Yes, please.
level 是掉到 n1是很快，就是 level 1很快。那 level 那这样子说，意思是说 level 3掉到 level 4速度也很快。 它可能留在 level 3啊，它不一定要掉下来到。
Right. But 如果你的电子留在 level 3， 还没有掉下来，它不会跟 n4 dot 相关，对不对？你就没有贡献到 n4， 你要掉下来才会贡献到它。
所以没有掉下来，它会变成是 n4 一直快速的被消失，电子就是从 n4 上。
分解动作有点像这样哈，它还留在这的时候，对它没有影响。掉下来的时候，理论上要加1嘛，但因为它很快就掉下去，所以它来不及加，它又消失了。所以这边就好像一个没有改变它的量一样。
所以 level 4等是几乎没有电子。
Almost like a constant， 不是 zero， 它是一个 constant。Constant derivative is zero, but itself is non-zero。
为什么constant？ 那 constant 不就是因为你马上掉下去，马上掉。
就是 level 4到这么高是不会累积任何东西啊。
That's another point 啊，我本来只是要 justify 微分为零，所以它只需要常数就可以 justify， 它不需要本身也为零，但是它本身是不是不只是常数，而且也是零，我们可以再进一步讨论啊。但这里我的数学模型只需要它是常数就可以，不需要它本身是零。OK， 当然它这个常数也很小啊，就像我们的。就算它不是零也很小，所以我们在这个 approximation 里面不是把它拿掉了吗？就是它够小，所以相对于其他的，比如特别是 n3 来比，这个加就好像只有它一样。我们已经用了这个 approximation。Please。
n2 大的情况应该也跟 n4 大的像，那为什么只想要 n4 大的，不用想要 n4？
我好像没有动用到 equation 2来，我一路解下来，我没有用到第二式嘛，对不对？那你有兴趣，你可以把第二式也用进去，用同样 approximation， 看看会不会得到不一样的 solution。我这边好像只用了其中3个 equation， 就把结果写出来。Yes。
因为那个，Tau 4到1是非常大的， 不是非常小的，所以就是N4 比上 tau C 就是会非常大。但像 Chris 就是相当于就是它一旦是个 constant， 那它就会往1跃迁。
N4是一个小数，tau C 也是一个小数，但是，所以你除起来，你现在不知道到底。
不知道谁的级别。
对，不知道谁跟那个。只是我想问的是说，如果是N4它是一个常数的话，那它不是非零常数的话，那你说的就是马上它掉下来，然后掉下去，这个并不是对的。
Good。对，我想过这个问题。这个 model 对，我必须承认它不是非常的 rigorous。那它唯一的任务是给我们一个 single differential equation， 而且可以有解析解。因为如果这些都不排除，我没办法得到这样的 equation， 我势必要留在联立微分方程组的状态下去解它。那我就没有办法得到一个简单的模型，告诉你它大致的行为。这边用到很多近似符号哦，这边都是近似，这不是一个非常严格的 model. But if you don't use it, you have no analytic solution. It's very difficult to get insight about what happens in the light matter interaction. If you are interested in rigorous solution, yes, it's okay. You can resort to the numerical solution. But I believe to some extent, it would be very close to the simple model we obtained.